Have you ever looked at a massive bridge or a skyscraper and just wondered, what's actually holding all of that up? Well, it all comes down to an invisible world, a hidden battle happening inside every single piece of material. So today, we're diving into that world of stress and strain. It's the language that tells us if something is going to stand strong or if it's going to break apart.
So let's start with a simple question. Imagine you have a solid steel rod, and you're pulling on both ends with a huge amount of force. How does it fight back? What's going on inside that lets it resist being torn into? It's definitely not magic. Turns out the answer is that invisible battle we were just talking about. Inside that steel, every particle, every atom is creating an internal force to fight back against being pulled apart. And today, we're going to make that invisible fight visible. To really get what's going on, we have to imagine we have this superpower, right? The ability to just slice right through the material and see the internal forces that are holding everything together. And that internal resistance, that fight, it has a name. It's called normal stress. It's basically a measure of how much internal force is pushing or pulling across that imaginary slice we just made. It's the material basically screaming, nope, I am not going to break.
Okay, so defining it is one thing, but for this to be useful to, engineers building things, we have to be able to measure it. And the great news is, the math behind it is actually pretty straightforward. The core formula is just beautiful in its simplicity. Stress, which we represent with the Greek letter sigma, is just the force applied, which we call P, divided by the cross-sectional area, A. That's it. It's all about how much force is concentrated in a certain area. The more force you pack into a small spot, the higher the stress.
Now, this normal stress, it comes in two main flavors. First, if you're pulling a material apart, that's called tensile stress, or just tension. That causes the material to stretch, and we call that a positive stress. The other flavor is when you're squeezing it together. That's compressive stress, or compression, which makes it shorter. And you guessed it, we call that negative. So how do we talk about these numbers? Well, in the metric system, the base unit is the Pascal, but a Pascal is super tiny, so you'll almost always hear about megapascals or gigapascals. Here in the US, it's usually pounds per square inch, or PSI. And just to give you some context, 1 PSI is almost 7,000 pascals, so these numbers can get big pretty fast. Okay, so that's stress, the internal force. But what's the actual result of that force? What happens to the material itself? Well, that brings us to the other half of our dynamic duo, strain. If stress is the cause, then normal strain is the effect. We use the Greek letter epsilon for it, and it's really just a way to measure how much something deforms, how much it stretches or squishes compared to its original size. And here's the key thing. It's a ratio, so it's dimensionless, which is just a fancy way of saying it has no units. And hey, just like stress, the formula is super simple and makes total sense. Strain equals delta, that little triangle, which just means the change in length, divided by L, the original length. It's basically just the percentage of how much it's stretched. Now let's say you do the math for a big chunk of steel under a heavy load. You might end up with a number that looks like this. Kind of underwhelming, right? It looks so small, almost nothing. But that tiny number tells you everything. A strain of 0.0007 means that a 2-meter-long steel bar, that's about 6.5 feet, only stretched by 1.4 millimeters. That's it. It shows you just how incredibly stiff and strong these materials really are. All right, now for a quick but really important point. Those simple formulas we just looked at, they work perfectly, but only if you follow a few rules of the game. There are some key assumptions we have to make. So for that super simple formula, stress equals force over area, to really be accurate, a few things have to be true. The object needs to have the same cross-section all the way down. The material has to be the same stuff all the way through, and, this one is critical, the force has to be pulling right through the dead center. If you pull on it off center, you start to get bending, and trust me, that's a whole different can of worms. Okay, enough with the theory. Let's put all this together and see what these numbers actually look like in a couple of real-world engineering examples. So check this out. For a simple rectangular bar being pulled, we're seeing a stress of 87.5 megapascals. Now look at the piston rod. On the upstroke, when it's in tension, it's feeling a stress of over 8,000 psi. But look what happens on the downstroke. When it's in compression, the stress is way, way lower. This is exactly the kind of analysis engineers do all day to make sure parts are designed correctly. So, what's the big takeaway from all this?
It's that stress and strain, they aren't just numbers in a textbook. They are the fundamental language that lets us understand and, more importantly, predict how any material is going to behave when you put a load on it. It's truly the foundation of all modern engineering.
By understanding this language, we can build amazing things that are safe and that last. But it also leads us to the ultimate question, doesn't it? What is the limit? What happens when that internal battle gets to be too much and the material just can't handle the stress anymore? Well, that's a story for another time.